In a young universe, a giant can be silent. Tonight's journey follows a sleeping black hole with a mass near 400 million suns. Its light is muted, its gravity is not. Drift through dusty halos, faint filaments and quiet rings of gas. Watch how motion leaves clues when the centre refuses to shine. If this kind of calm science storytelling helps you relax, please tap like and subscribe for more long sleep-ready cosmic documentaries. Now let the darkness soften, let the details unfold. A distant young galaxy holds a quiet centre that outweighs almost everything around it. The anchor is simple and unsettling. A black hole of about 400 million solar masses sits there while its light stays faint. In that region, darkness is not empty. It has weight and structure. A shallow glow surrounds the core and fades inward through a soft gradient. The brightness does not peak into a harsh spike. It settles like snow over a mountain ridge that remains hidden beneath a smooth surface. At this distance, the story begins with what fails to appear. A strongly feeding centre would blaze and heat its surroundings into sharp contrasts. It would strip dust from inner zones and leave hard boundaries of light. Instead, the central radiance remains restrained, and the nearby material keeps cooler layers. That calm absence becomes the first payoff. A very large mass can exist without announcing itself as a beacon. The sky can hide giants when the fuel trickle stays low. Sleeping describes a physical budget rather than a mood. Accretion means matter drifting inward under gravity. An accretion disk is a flattened flow where gas circles shears and warms. When the inflow is small, heating is limited and the light stays modest. The disk can remain faint and partly veiled by dust that scatters and softens the glow. A slow visual anchor settles into focus. A pale ring of cooler gas encircles the centre, and its inner edge looks more defined than its outer fade. Rotation is fastest near the middle and gentler farther out. That change draws a spiral of motion rather than a rigid wheel. Light behaves as a tracer of that motion. A signal would smear slightly where speeds differ most along the line of sight. The pattern points to a compact pull that starlight alone cannot explain. Here the number becomes the heart of the surprise. 400 million solar masses means a gravity well beyond everyday intuition. It equals the mass of 400 million suns gathered into a region smaller than any star cluster. The comparison stays plain and physical. It resembles a vast coastline made of countless grains of sand, with each grain standing for a sun. All that mass is concentrated into one deep basin with no solid surface. Another payoff arrives when the quiet is taken seriously. If the centre is dim now, growth does not need to be constant. It can surge for short spans and then rest for long spans. During rest, the disk cools and dust settles back into layered bands. The host galaxy can look ordinary again while the central mass remains. In that way, a single quiet giant hints at a wider population of quiet giants. Many could pass unnoticed when brightness is the only searchlight. Quiet does not mean still. The disk keeps a texture of ripples where faster inner layers slide past slower outer layers. Small density waves pass through the ring and fade. Where gas becomes slightly thicker, the glow brightens by a small amount. Where it thins, the glow dims again. These gentle changes offer another payoff. Even a sleeping centre leaves measurable fingerprints in shape and gradient. The fingerprints come from gravity and from the slow conversion of motion into heat. In that region, light scatters off dust grains and changes direction many times. That scattering smooths sharp edges and turns bright knots into soft patches. The result is a calm map of brightness that feels almost continuous. A second visual anchor forms across the galaxy's small body. Starlight filters through a thin haze, and the glow appears soft and uneven. Patches dim where dust scatters light, then brighten, where the haze thins. No narrow beam cuts across the scene and no blazing centre washes the surroundings. The structure looks compact and still assembling. Even so, a mass this large should shape the whole system. The response can be subtle rather than dramatic. Outer gas can drift in slightly shifted paths, and inner gas can settle into a flatter plane. The scale shift stays gentle. The view moves from the thickness of a dusty ring to the sweep of a forming galaxy. Then it moves again into time. The universe is about 800 million years old in this scene. That is early, like a first calm morning compared with a long day. In this era, galaxies assemble fast and their ingredients arrive in uneven streams. Orbits rearrange and small systems merge into larger ones. A massive black hole appears inside that churn. Its quiet state suggests the churn includes long pauses as well as bursts. Another payoff clicks into place from the timeline. A giant that already exists this early implies either rapid early feeding or a heavy starting seed. Both options change how the first structures are imagined, yet the centre is not bright enough to make the answer obvious. The limit of observation enters softly here. A dim core is hard to read at great distance. Dust can mimic faintness by absorbing and re-radiating energy into longer wavelengths. Distance can smear detail so separate regions blend into one blur. The motion of gas can be inferred only indirectly through broadening and shifting of light. The limit is specific. The mass estimate depends on models that connect brightness and motion to gravity in a setting that cannot be resolved cleanly. Even so, the broad conclusion remains sturdy at the level of magnitude. The mass is enormous for such an early epoch, and the light is low compared with that mass. Even if the exact value shifts, the mismatch stays. That mismatch is the doorway to the deeper arc of the journey ahead. It raises three calm questions with immediate stakes. How does such a mass form quickly? How does such a mass remain faint? How many others remain hidden by distance and dust? A final visual anchor slows the pace again. The inner ring appears like a faint contour line around a deep hollow. The hollow is not a hole in space, it is a region where paths curve inward and time feels stretched by gravity. Gas drifts along those curved paths, warms gently, then cools as it spreads outward again. The brightest point never overwhelms the scene. The centre is present as a pull, not as a glare. The next step turns to the clock itself and to why early time matters. The path moves from this muted glow to the wider era that surrounds it. A quiet giant becomes stranger when the calendar is set in the early universe. The anchor is that the scene unfolds about 800 million years after the beginning, like the first thin glaze of ice before a long winter deepens. In that era, matter has had little time to settle into stable shapes. The large scale is still rearranging itself. Small clumps pull together and then drift apart again. Light behaves as a delayed message that carries both distance and age. The deeper the distance, the earlier the snapshot. The first payoff arrives with that simple rule. Looking far away means looking back even when the source remains faint. The sky becomes an archive of young stages. A visual anchor forms in the darkness. A sparse field of newborn starlight sits inside a soft veil of dust. The glow is uneven and gentle. Some patches brighten where gas grows denser. Other patches dim where dust scatters the light into a wider haze. The whole galaxy looks compact, its edges are not sharp, They fade outward like breath on cold air. At this distance, fine detail refuses to appear. The scene invites a slow approach. The view moves from the whole faint body to the way its light shifts in colour. One concept guides the shift. Redshift means light is stretched by cosmic expansion. It is a change in wavelength, not a change in intent. A simple analogy keeps the idea calm and physical. It resembles ripples on a pond that slowly lengthen as the water drifts outward. The ripples still arrive, their spacing is simply wider. The second payoff lands quietly. A stretched signal tells time as well as distance. It allows an estimate of how young the universe is at the moment of emission. Yet the light does not travel through empty space. It crosses gas and dust that are not evenly spread. Dust becomes the second concept. Dust is tiny, solid grains mixed into gas. It scatters and absorbs light. Then it re-emits energy at longer wavelengths. The effect is soft and soothing. Bright regions can look dimmer than they are. Edges can look blurred. A visual anchor deepens. A faint core sits behind layered veils. The inner glow is not a point. It spreads into a small oval. The oval has a brighter rim on one side, the other side fades into darkness. That unevenness hints at dust lying like a thin curtain. The curtain is not flat. It has ripples and folds. The folds create gradients in brightness. The third payoff appears in the shape. Even without sharp detail, the light can hint at structure. A compact center can be inferred from how the glow concentrates. A surrounding envelope can be inferred from how the light softens outward. The view shifts scale again. It moves from the width of a dusty patch to the span of intergalactic space. Between galaxies, gas is thin but not absent. It can leave faint imprints on travelling light. In that early era, the intergalactic medium is changing state. Some regions are more transparent, other regions remain more opaque. The change does not happen everywhere at once, it happens in pockets. That patchiness becomes a gentle checkpoint in the journey. The observed galaxy sits inside a region that is partly cleared. Light escapes more easily there. In a nearby region, the same light would be muted. The fourth payoff arrives as a caution. Brightness is not only about power, it is also about what the light must cross. A dim appearance can come from low feeding. It can also come from dust and intervening gas. The quiet giant sits inside that ambiguity. The limit of observation becomes clear and specific. The distance is so large that the galaxy spans only a small angle. Separate regions blur together. Measurements average light across multiple zones. Dust can hide the inner engine behind a smooth glow. Redshift shifts key features into wavelengths that are harder to separate cleanly. The limit is resolution and interpretation. The mass estimate rests on models that connect blurred light to motion and gravity. Even a strong model has broad uncertainty when the image is soft. If the magnitude remains meaningful, the center is too massive to ignore, and the light is too modest to call it fully active. Another visual anchor slows the pace again. A faint arc of emission traces one side of the inner region. The arc looks like a thin shell. It suggests gas arranged in a partial ring. The ring is not complete. It is interrupted where dust is thicker. The arc has a gentle brightness gradient along its length. That gradient implies uneven density. The scene holds still for a moment. The fifth payoff emerges from the arc. Early galaxies are not smooth spheres. They are layered and lopsided. Gas streams arrive from preferred directions. The streams can feed a center in bursts. Between bursts, the center can rest. Time becomes the calm bridge to the sleeping idea. 800 million years is long on an everyday scale. It is short on a cosmic scale. It is enough time for a massive center to grow if feeding is efficient. It is also enough time for feeding to stop and restart many times. A quiet phase can therefore be common. The story does not require constant brightness, it allows cycles. A final scale shift carries the mind from minutes of infall to hundreds of millions of years of assembly. Gas can drift inward over long spans. It can also be stirred outward by heat and turbulence. Dust can settle into thin layers and then be lifted again. The whole system can breathe in slow motion without any rapid flare. The next step turns from the calendar to the definition of sleeping. It moves closer to the inner flow and asks what low feeding looks like in matter and light. A giant mass is often imagined as a steady blaze, yet the center remains subdued. The anchor is that a low inflow keeps the inner flow cool enough that the light stays modest. In that region, gravity pulls with patience rather than spectacle. Gas circles and slowly loses energy. Only a small share reaches the tightest orbits where heating becomes intense. The first payoff settles quickly. A massive black hole can spend long stretches in a dim state without changing its mass. A visual anchor appears as an edge-on band of faint emission. A thin dark lane cuts through the glow where dust thickens. Above and below that lane a soft haze spreads like a delicate veil. The brightness does not spike at the centre. It rises gently toward an inner rim, and then fades inward into shadow. The shape suggests a layered flow rather than a single bright point. Light behaves as a map of temperature. Cooler zones radiate softly. Warmer zones brighten, but remain muted when fuel is scarce. The main idea is accretion rate. Accretion rate means the amount of matter drifting inward each year. When that rate is low, the hottest inner ring stays small and faint. The flow still rotates fast near the centre. Friction and shear still convert motion into heat. The difference is scale. The warm region does not spread far outward. It stays confined to a narrow band. A second payoff arrives here. The disk can look calm, not because nothing moves, but because the bright zone is limited in size. A natural analogy keeps the sense of flow without human imagery. It resembles a river in late summer that becomes a thin thread between stones. Water still runs and still shapes the bed. The sound and spray diminish because the volume drops. In that same way, a low inflow reduces the radiant signature without removing the underlying motion. A visual anchor slows again. The disk shows a gentle gradient from a faint outer skirt to a slightly brighter inner crescent. The outer skirt looks thicker as if dust and cooler gas puff upward. The inner crescent looks flatter as if the hottest layers settle into a thinner sheet. The boundary between them is not sharp, it is softened by scattering. Dust grains redirect light into wider angles. That makes edges look smoother and cores look broader. The next payoff comes from that softness. A dim state can be hidden further by dust. The true power can be partially shifted into longer wavelengths. The visible pattern becomes a blended portrait of heat and obscuration. The second concept adds a careful lever. Radiative efficiency is the fraction of falling mass turned into light. When efficiency is high, a small inflow can still shine. When efficiency is low, even a larger inflow can look dim. Efficiency depends on the inner flow shape. It depends on how close the gas orbits before it plunges inward. It also depends on how much energy escapes versus how much is carried inward as heat. A third payoff lands gently. A sleeping appearance can reflect either a low inflow, a low efficiency, or both. The sky then presents a quiet puzzle with calm rules. The disk offers physical clues. A thin inner ring suggests stronger cooling and tighter orbits. A thicker inner region suggests trapped heat and more turbulence. At this distance, such details blur. The pattern remains useful at the level of gradients and asymmetries. A visual anchor forms in motion rather than brightness. The faint glow shows a slight tilt. One side appears marginally brighter and sharper. The opposite side looks more washed and diffuse. That imbalance can come from geometry. A tilted disk shows a nearer side and a farther side. Dust on the nearer side can block more central light. Dust on the farther side can scatter light into a broader glow. The payoff is immediate. Even without seeing individual clouds, the disk orientation can change what looks active and what looks quiet. A gentle scale shift follows the flow inward. On small scales, atoms collide and exchange energy. Ions spiral in magnetic fields and heat by friction. On larger scales, entire gas streams feed the disk in slow arcs. Those streams bring angular momentum that must be shed. The shedding happens through turbulence and waves. It is a slow redistribution rather than a single drop. The calmness is not stillness. It is a controlled leak of energy across many layers. Another payoff appears when time is considered alongside flow. A dim phase can last longer than a bright phase. The mass can grow most during brief surges. Then the system can relax for long intervals. During relaxation, dust can settle into a thin mid-plane. Gas can cool into stratified layers. The inner bright ring can shrink and soften. The visible output can fall to about 1/100th of a natural bright ceiling for steady inflow. That fraction feels abstract until it is grounded. It's like a broad marshland that receives only a narrow trickle instead of a full flood. The basin remains. The waterline simply stays low. The limit of observation enters quietly and precisely. Accretion rate is not measured directly at great distance. It is inferred from light that has been stretched, scattered, and blended across regions. The inner disk cannot be resolved as separate rings. Dust can hide the hottest zone and reroute energy into wavelengths that overlap with cooler emission. Efficiency is also uncertain because the inner geometry cannot be seen. Models must assume a flow shape and an orientation. Small changes in those assumptions can shift the inferred inflow by large factors. The limit is degeneracy in modelling. Several combinations of inflow, dust, and geometry can produce similar faint patterns. Yet the broad conclusion holds. The system does not radiate like a strongly fed engine relative to its mass. The centre appears quiet compared with what that mass could produce under constant feeding. A final visual anchor returns to the layered disk. The midplane looks like a dark seam. Above it, a soft glow thickens into a faint wedge. The wedge fades with distance from the core. Its outer edge dissolves into the galaxy's broader haze. The inner edge remains more defined, like a shoreline of warmth around a deeper shadow. The transition forward stays gentle. The next step moves closer to the boundary where gravity becomes absolute. It follows how motion and light can reveal an unseen edge without forcing the scene into glare. At this distance, the deepest boundary does not shine and still defines the entire scene. The anchor is that an event horizon is known by what nearby light and motion cannot do. The inner flow looks calm, yet the geometry becomes strict near the centre. A dark core sits inside a brighter ring. The ring is not uniform. Its near edge appears softer. Its far edge looks slightly sharper. A thin gradient runs across the glow. The gradient hints at temperature and speed changing with radius. The first payoff settles at once. A boundary can be mapped without being seen because gravity shapes every path around it. The key term is event horizon. An event horizon is the one-way boundary for light. That definition stays brief, then returns to imagery. The boundary resembles the edge of a deep, still sinkhole in limestone. The rim looks ordinary. The interior removes all return. The rim matters because motion near it becomes extreme. Gas circles faster as it spirals inward. The ring tightens. It thins, it warms. Light behaves as a messenger that carries the imprint of that tightening. A signal would change in colour and timing as it climbs away from strong gravity. This is gravitational redshift. Gravitational redshift means gravity stretches light as it escapes. The second payoff arrives with a simple consequence. Even if the inflow is low, the inner ring can look dimmer than its heat suggests because part of the light loses energy on the way out. A visual anchor forms as a slow sweep across the inner disk. The disk appears like a shallow bowl. The bowl has a bright inner rim and a darker centre. A faint arc appears above the rim on one side. The arc is not a separate object. It is light bent from the far side into view. The arc looks like a thin brushstroke laid over darkness. This bending is gentle in description and strong in meaning. The third payoff becomes clear. Gravity can redirect light so that the far side is partially visible even when the centre stays hidden. The scene holds a physical detail that remains concrete. The brightness drops sharply across a narrow zone near the centre. The drop is not a smooth fade. It is a steeper edge that marks where the flow changes character. Inside that edge, the disk becomes thinner or less luminous. Outside it, the disk keeps a broader surface of glow. A single number grounds the scale without forcing detail. The event horizon size is about 1 billion kilometers. That is like a circle that could fit inside the orbit of an inner planet. The comparison stays every day in spirit. A vast region can still be small compared with a galaxy. The scale shift follows with calm. The view moves from a boundary measured in billions of kilometers to a galaxy measured in light years. The boundary remains central because it controls where light can still leave. Another payoff arrives when time is added. Near the horizon, the inner flow changes over short intervals. Farther out, the disk changes more slowly. Yet the distant view averages many changes into one soft image. The image becomes a slow portrait of a fast place. The disk is not a rigid wheel. It has shear. Inner layers slide past outer layers. Waves travel through the gas. Some waves compress the gas into thin, bright lanes. Others stretch it into dim gaps. The lanes curve into partial spirals. The spirals soften as dust scatters light. A visual anchor returns in a different form. The inner rim looks like a narrow shoreline of warmth. Behind it, the darkness appears smoother and deeper. The rim has a slighter symmetry. One side is brighter, the other side is dimmer and broader. The asymmetry can come from motion. Gas moving toward the viewer would shift light slightly. Gas moving away would shift it the other way. Even without resolving the shifts, the brightness can hint at direction. The next payoff is immediate. Motion can be inferred from patterns, not only from sharp lines. The disk then becomes a rotating map of gravity. The second concept of the section joins the first without crowding. Photon paths curve in strong gravity. Curved paths mean the scene includes light from places not directly facing the viewer. The far side contributes a faint glow. The near side can be partly muted by dust. The result is a crescent-like emphasis around the center. The crescent is not a sign of appetite or intent. It is a consequence of geometry and scattering. A calm analogy keeps the picture stable. It resembles a smooth shell of ice on a pond with a darker hole beneath. The shell catches light at the rim. The hole remains dark even when the shell glows. The analogy stays natural and quiet. It avoids agency. The payoff follows. A ring can appear even when the center emits little because the ring is where energy and visibility concentrate. The section now reaches the limit of intuition and observation. The event horizon cannot be imaged directly at such distance. The light is faint, the galaxy is small on the sky. Many regions blend into one. The inner rim and the outer disk overlap in projection. Dust adds further confusion by absorbing and re-emitting energy. The model must guess how thick the dust layer is. The model must also guess the disk tilt. Small changes in tilt can change how bright the far rim appears. The limit is degeneracy. Several different inner geometries can produce the same softened crescent. The boundary is real, but the exact outline cannot be drawn with certainty. Another payoff arrives through that humility. The horizon remains a robust idea because it predicts a family of patterns, not a single sharp picture. It predicts a dark center. It predicts a brighter rim. It predicts bent arcs. It predicts redshift that dims escaping light. The details can vary while the logic holds. The visual anchor deepens one last time. A thin, bright arc hugs the inner rim like a delicate filament. Beneath it, the center stays dark and smooth. Around it, the disk fades outward in layered bands. The bands look slightly thicker above the midplane. They look thinner near the brightest rim. A soft gradient runs from warm to cool. The gradient becomes a calm signature of distance from the center. The scale shift returns in time. A single orbit near the rim can be brief. A full growth cycle of the galaxy spans millions of years. The distant view compresses both into one quiet frame. The transition forward remains gentle. The next step turns to a ceiling on brightness that comes from light itself. It moves from the hidden boundary to the balance between inward gravity and outward radiation. A bright engine has a natural ceiling even when gravity keeps pulling inward. The anchor is that too much light can push gas outward and slow feeding, setting a calm balance. In that region, outward pressure meets inward weight. The balance is not perfect. It is a tendency that shapes what is common and what is rare. A visual anchor appears as a luminous inner ring that never becomes a blinding point. The ring looks thin and smooth. Its edge is brighter than its center. A faint halo surrounds it and fades into the darker disk. The halo is not sharp. It is softened by scattering in the nearby gas. The first payoff arrives quickly. A quiet phase can be long because brightness itself can discourage steady inflow. The key term is Eddington limit. The Eddington limit is a brightness where light pressure balances gravity. That definition stays brief, then returns to plain imagery. When radiation is strong, it pushes on electrons in the gas. The push is gentle at low brightness. It becomes serious when brightness rises. A natural analogy keeps it calm and physical. It resembles a dandelion seed in still air. A weak breeze lets it drift downward. A stronger breeze holds it up and keeps it from settling. In the same way, strong radiation can keep gas from settling inward. The second payoff follows. There is a reason constant blazing growth is difficult to sustain. The universe builds in pulses because balance forces breaks. A single number grounds the scale without crowding the mind. For a mass of about 400 million solar masses, the Eddington limit is about 5,000 trillion times the sun's brightness. The comparison lands as a simple picture. It is like adding the glow of many thousands of galaxies similar to the Milky Way into one point of light. The number is immense, yet it is a ceiling rather than a guarantee. A sleeping appearance suggests the system sits far below that ceiling for now. The disk still glows. It just does not approach its possible peak. Another payoff appears when the ceiling is turned into a growth clock. If the system fed steadily, right at that ceiling mass would rise quickly on cosmic time. If the system stays below the ceiling, most of the time growth slows. This makes long quiet intervals not only possible, they become expected. A visual anchor deepens. A thin inner rim appears brighter on one side. The opposite side looks slightly wider and dimmer. The halo above the disk looks thicker than the halo below. That asymmetry can come from tilt and from dust. It can also come from uneven heating. Where inflow is stronger, the ring warms and brightens. Where inflow is weaker, the ring cools and dims. The third payoff sits inside that asymmetry. Feeding is not a symmetric drizzle. It arrives along preferred lanes. The lanes shift and fade. The center can remain quiet even while gas exists nearby. The second concept enters with care. Opacity describes how easily radiation pushes on gas. Opacity is resistance to light passing through matter. In dusty gas, opacity can be higher. In ionized gas, opacity can be different. This matters because the Eddington balance depends on how strongly light couples to matter. A change in opacity shifts the effective ceiling. In a dusty environment, outward push can act farther from the center. In a cleaner environment, gas can slip inward more easily. The payoff is immediate. The same mass can behave differently depending on the surrounding mixture. The ceiling is not a fixed number in practice. It is a soft limit shaped by composition and structure. A visual anchor returns to structure at the boundary between warm and cool layers. The inner ring looks flatter. The outer disk looks puffed as if supported by heat and turbulence. A narrow transition band separates them. The band shows a smooth gradient of brightness. That gradient hints at temperature changing with radius. It also hints at gas density changing across a small distance. The scene becomes a quiet laboratory of balance. Gravity tries to compress. Heat tries to expand. Radiation tries to push. Dust tries to hide and scatter. The scale shift arrives gently. On the smallest scales, individual electrons receive tiny nudges from photons. On larger scales, entire clouds feel a steady outward pressure. Over millions of years, that pressure can clear channels and leave cavities. Those cavities can reduce feeding later. A fourth payoff emerges. A bright episode can plant the seeds of a later quiet episode. The center can dim because it earlier pushed its fuel outward. The story of sleeping then includes memory. The environment remembers past brightness in its structure. The limit of observation enters with clear edges. The Eddington limit is a theoretical balance, but the true inflow is inferred indirectly. Brightness can be hidden by dust. Energy can emerge at wavelengths that blend with other emission. The inner geometry cannot be resolved at great distance. A thick disk can trap radiation and let some energy be carried inward. A thin disk can radiate more efficiently. Both cases can produce similar apparent brightness after dust and distance are included. The limit is model dependence. The ceiling can be estimated, yet the true fraction of the ceiling remains uncertain without direct access to the inner flow. Still, the concept is useful because it frames what is plausible. It suggests that if the system ever approached its ceiling, it would likely do so briefly. It would then ease back into quiet. Another payoff follows from that framing. A sleeping giant does not contradict rapid early growth. It can follow it. The giant can grow in short bright spurts that stay near the limit. Then it can spend long spans far below the limit. The average appearance becomes calm even if the history includes rare intensity. A final visual anchor settles the scene. The inner ring glows like a thin collar around darkness. Around it the disk fades into a broader haze. The halo looks layered as if stacked sheets of thin mist float above the midplane. The brightest edge never floods the scene. It remains contained. The transition forward stays soft. The next step turns from ceilings to clocks. It asks how such a large mass can form so early if growth is limited by balance. A calm glow becomes a timing problem when the mass is already enormous in a young universe. The anchor is that growth must either be fast at times or begin from a heavier starting seed. At this distance, the calendar presses gently on every explanation. 800 million years is not much time for slow accumulation. A massive center needs either long steady feeding or short intense phases. The first payoff lands simply. The quiet present does not erase a bright past. A visual anchor forms in the space around the galaxy. A narrow filament of gas drifts in from the dark. It is slightly brighter along its spine. It looks like a pale thread laid across emptiness. Near the center, the thread bends. It curves into the disk plane and fades into a thicker inner haze. A faint crescent of warmer emission appears where the stream meets the disk. The crescent marks a shock front where flows collide and compress. That physical detail matters. A boundary of compression can turn motion into heat without requiring a constant blaze. The first concept is exponential growth. Exponential growth means the growth rate rises with the mass. A simple analogy holds it in place. It resembles a crystal in a cooling pond that gains new layers faster as its surface expands. Early layers are slow. Later layers can appear quickly once the framework exists. The second payoff follows at once. A large mass can be easier to grow than a small mass if fuel arrives. The second concept provides the clock. Salpeter time is the mass doubling time at Eddington feeding. The number is about 50 million years. That is like a slow cycle of major climate shifts on Earth. It is long in a day. It is short in cosmic history. The third payoff arrives through that comparison. A few doublings can happen within a young universe if feeding stays near the ceiling. The mind can trace the arithmetic without strain. Doubling repeats. After one doubling, mass doubles. After many doublings, mass becomes huge. The calm difficulty appears here. A massive center needs many doublings from a small seed. It needs fewer doublings from a large seed. The seed is the starting mass. The seed can be light or heavy. A light seed begins as the remnant of an early massive star. A heavy seed begins as a direct collapse of gas into a compact core. The section keeps only these two routes as guiding images. The fourth payoff appears as a choice. Either the seed is heavy or the duty cycle is high. Duty cycle means the fraction of time spent in bright feeding. It can be small for a sleeping present. It can be large for rapid early growth. A visual anchor returns to the inner disk. The disk shows layered bands. The outer bands are cooler and thicker. The inner band is thinner and warmer. Between them sits a narrow transition with a clear brightness gradient. That gradient is a physical record of where heating changes. The stream that feeds the disk can arrive off-center. It can twist into a spiral. It can deposit angular momentum that must be shed. That shedding takes time. Gas does not fall straight in. It circles, it forms a ring. It develops waves that transport momentum outward. The next payoff comes from that motion. Feeding is not only about supply, it is also about the ability to shed rotation. A heavy seed helps because it deepens the central pull early. A high-duty cycle helps because it keeps pressure and turbulence engaged in moving gas inward. Yet both routes face limits. Radiation can push back, dust can block, turbulence can puff the disk and make inflow less efficient. The filament itself can be unstable. It can fragment into clumps. Each clump can arrive as a brief pulse. That pulse can brighten the inner ring for a while. Then the ring can cool. The scene can return to quiet. Another payoff settles quietly. Bursts can do most of the growth while quiet dominates the appearance. The scale shift becomes soft and steady. On small scales, ions collide and share energy. Magnetic fields guide some flows. Heat rises through layers and then escapes as radiation. On larger scales, filaments deliver mass across tens of thousands of light years. Over millions of years, the galaxy rearranges and new filaments connect. Over tens of millions of years, a doubling clock can tick. Over hundreds of millions of years, many clocks can tick if conditions permit. The sleeping present sits at the end of such ticking. A visual anchor deepens in the inflow zone. The filament has a sharp edge on one side. The other side is diffuse. That edge suggests shear where the filament meets a different medium. The shear can roll into waves. Those waves can mix material and thicken the stream. Near the disk, the stream flattens into a ribbon. The ribbon meets the disk at an angle. The collision region glows as a thin crescent. It is not a flare. It is a persistent seam of compression. The payoff arrives as a physical clue. A seam implies supply, a seam implies recent delivery. The system can be sleeping and still connected to fuel. The limit of observation enters gently and precisely. The earliest phase cannot be watched directly in real time. The view is a single snapshot. The duty cycle cannot be measured from one image. The seed mass cannot be seen inside the glow. The inflow history must be inferred from models. Those models depend on dust content and disk orientation. They also depend on how efficiently energy escapes. Small changes in assumed efficiency can change inferred growth time. The limit is the unknown past. The present light does not uniquely determine the earlier light. Yet the logic remains useful. A mass of 400 million solar masses at such an early time constrains histories. It favours either a heavy seed or long near ceiling phases. It allows a mix of both. Another payoff follows from that constraint. The sleeping label becomes a phase within a broader life cycle, not a permanent state. The scene can be calm now because the environment has recently been heated and then cooled. It can be calm now because fuel is temporarily diverted into outer rings. It can be calm now because radiation earlier cleared a cavity and inflow is rebuilding. Each option is compatible with the same faint glow. Each option predicts something about variability and structure. The structure is the more accessible clue. If filaments exist, supply can return. If dust lanes thicken, hidden feeding can occur. If the inner ring is thin, efficiency may be high during bursts. If the inner region is puffed, radiation may be trapped and escape later. A final visual anchor settles the mind. The galaxy remains compact and softly lit. The filament thread continues to feed the inner haze. The crescent seam of compression stays faint and steady. The dark core remains present as a missing center inside the ring. The transition forward stays gentle. The next step turns from clocks to episodes. It follows how growth can arrive in bursts without keeping the center bright for long. In that region, the brightest growth can arrive in short arrivals and still leave a long, quiet face. The anchor is that bursty accretion can build a giant quickly, while most of its time remains dim. The disk does not need to glow steadily to gain mass. It needs moments when supply and transport align. A visual anchor settles over the inner few light years. The faint disk shows a set of narrow lanes. Each lane curves inward and then breaks into knots. The knots look slightly brighter than the surrounding haze. Between knots, the glow thins into darker gaps. The pattern resembles beads on a curved thread, yet the thread itself remains soft and dusty. The first payoff arrives in the spacing. Clumps mean delivery happens in parcels rather than in a smooth pour. Each parcel can trigger a brief rise in heating. Then the disk can cool again. The core returns to a subdued state while the mass continues to grow in the long run. The first concept is duty cycle. Duty cycle means the fraction of time spent in bright feeding. A low duty cycle allows a sleeping appearance. A low duty cycle can still produce large growth if each bright interval is strong. The second payoff follows at once. The sky can show a quiet giant even if its past includes repeated bright episodes. A natural analogy holds the rhythm without using human imagery. It resembles a tide pool on a rocky shore. Water rushes in at high tide, then it retreats and leaves stillness. Over many cycles, the pool is reshaped even though most moments are calm. In the same way, repeated inflow pulses can reshape the central mass. The disk's surface can look quiet between pulses. A visual anchor deepens along a spiral lane. A denser clump enters the disk plane and stretches into a curved ribbon. The ribbon shows a sharp leading edge. Behind it, a softer tail fans out and fades. Along the leading edge, a thin compression line forms. The line is slightly brighter and more defined than the rest. This physical boundary matters. Compression converts orbital motion into heat. Heat can raise emission briefly. The third payoff settles into place. Bursts do not require chaos everywhere. They can begin at a narrow seam where a clump meets a rotating layer. The second concept arrives with gentle clarity. Angular momentum is the tendency of orbiting gas to keep circling. Gas cannot fall inward unless angular momentum is moved outward. That movement happens through waves and turbulence. In a smooth disk, the transport can be slow. In a clumpy disk, shocks and density waves can speed it up for a while. A knot compresses, a wave travels outward. The inner ring receives new material. A brief bright interval can follow. Another payoff appears in that chain. Bursts are not only about supply, they're also about the disk's ability to pass momentum along. A supply pulse without transport can stall in an outer ring. A transport pulse without supply can fade quickly. A burst is the overlap of both. The scene holds steady as the disk breathes through structure rather than through light. A visual anchor forms closer in. The inner rim looks thinner during a bright interval. The rim becomes a more defined arc. The arc wraps around the dark center like a narrow contour line. Outside it, the disk looks slightly dimmer, as if energy has concentrated inward. When the pulse ends, the arc softens again. The rim broadens. The glow spreads back into a wider haze. The fourth payoff arrives in that calm reversal. The same disk can switch appearance without changing its underlying mass by much. Light responds quickly to heating. Mass responds more slowly to accumulation. The scale shift becomes gentle. Near the center orbital, times can be short. The inner flow can change within years. Farther out, rings evolve over thousands of years. The duty cycle emerges over millions of years. The full assembly unfolds over hundreds of millions of years. A quiet image is a time average of many rhythms. The single snapshot captures the average face, not the full heartbeat. Another payoff settles with that scale shift. A sleeping label describes an era of observation, not a permanent condition. The disk can spend most of its time between pulses. It can still gather most of its mass during brief peaks. The section now holds one number to anchor the sense of pace. A bright burst can last about 10 million years. That is like the time it takes a mountain range to rise by a small amount. It is long for a living system and short for a galaxy. During 10 million years, a near-ceiling phase can add large mass. During the longer quiet intervals, the disk cools and thickens. Dust returns to the mid-plane. The glow softens. The center looks calm again. A visual anchor shifts outward to the fuel lanes. A filament feeding the galaxy shows a braided texture. One strand is denser and brighter. Another strand is fainter and more diffuse. Where strands meet, a knot forms. The knot drifts inward along a curving path. Its leading edge becomes sharper as it enters the disk. Its interior becomes more opaque. Light behaves as a softened glow around the knot. Some light is absorbed, some is scattered into a wider halo. The fifth payoff appears as a subtle warning. Brightness can underestimate inflow when knots are opaque. A strong pulse can be partly hidden by dust and thickness. A dim appearance can mask a stronger event that is wrapped in obscuration. The limit of observation becomes specific and gentle. Bursts are events in time. The distant view is a single frame. Time variability cannot be measured directly from one snapshot. Short intervals blur into averages. Dust adds another layer of uncertainty by shifting energy into bands that overlap with cooler emission. The inner rings cannot be separated cleanly at this distance. Models must assume a duty cycle distribution. They must assume how often knots arrive. They must also assume how quickly the disk cools after heating. The limit is the missing timeline. Several different burst patterns can produce the same present quiet glow. Yet the idea remains powerful because it matches both constraints. It allows rapid early growth. It also explains the sleeping present. Another payoff arrives in the disk texture. Clumps and seams imply episodic feeding is plausible. The disk is not uniform. It contains pathways for pulses. It contains boundaries where shocks can form. It contains gradients that can shift as knots pass. The quiet giant becomes less mysterious when growth is allowed to be intermittent. The closing visual anchor settles into the inner haze again. The arc at the rim is faint. The dark center remains smooth. The outer disk holds soft bands and scattered knots. The whole system looks like a calm surface that occasionally receives deeper swells. The transition forward stays gentle. The next step moves from bursts to what happens when a burst becomes too dense. It follows how light can become trapped and delayed inside thick inflow. At this distance, brightness can be delayed when the inflow becomes thick enough to hold its own light. The anchor is that trapped radiation can let mass move inward fast while the glow stays muted. The scene begins with a disk that looks heavier than it looks bright. A visual anchor forms as a swollen inner region. The disk is no longer a thin sheet. It rises into a gentle mound. Its surface shows faint striations like layered bands of slightly different brightness. A darker lane cuts across the mid-plane. Above that lane, a pale halo extends outward and fades. The first payoff arrives at once. A dim face can hide a dense interior. Dense inflow changes the path that light can take. The first concept is optical depth. Optical depth is how hard light finds a way out. When optical depth is low, photons leave quickly. When optical depth is high, photons scatter many times. They wander. They lose direction. The analogy stays calm and natural. It resembles moonlight inside a thick sea fog. The light still exists. It spreads and softens. It takes longer to reach open air. The second payoff follows. A bright engine can be smoothed into a faint glow if photons are delayed and redirected. The physical detail becomes clearer. The inner mound has a sharper outer edge. Beyond that edge, the disk becomes thinner. The edge looks like a low cliff in brightness. Inside the edge, the glow is diffuse. It is as if the surface is illuminated from within rather than from a single ring. Light behaves as a diffusing field. A signal would emerge as a broad soft patch instead of a crisp line. This changes how feeding and shining relate. Mass can move inward with the flow, light can lag behind. The second concept joins without crowding. Photon trapping means radiation is carried inward with the gas. The definition stays brief. Photon trapping is light carried inward by inflow. Then the narrative returns to imagery. In a thick inner disk, gas moves inward faster than photon can escape. Photons bounce and scatter. The inflow acts like a slow conveyor of energy toward the center. Some energy is swallowed behind the horizon. Some leaks out later and farther out. The third payoff lands gently. The usual brightness ceiling becomes softer when light cannot push back effectively. Radiation pressure depends on escaping photons. Trapped photons cannot push outward in the same way. Growth can briefly exceed the familiar steady balance without producing a matching glare. A single number anchors the idea in time. In the thickest case, photons can take about 100,000 years to diffuse outward. That is like a long interval of slow erosion shaping a cliff face. It is short in cosmic history. It is long compared with rapid inner changes. The payoff is immediate. Light can arrive late compared with mass transport. A burst can add mass first. The bright signature can be delayed or muted. A visual anchor deepens into the disk's surface. The mound shows a faint spiral ridge. The ridge wraps inward and then dissolves. Along the ridge, a thin seam is brighter. The seam marks compression where the flow thickens. The seam also marks where opacity rises. Dust and ions make scattering stronger. The ridge becomes a wall of wandering light. Outside the mound, the disk remains cooler and thinner. It radiates more efficiently. Energy that leaks out can show up there. The glow can therefore appear offset from where the mass is moving. Another payoff follows. A sleeping appearance can be a geometric illusion of where radiation escapes, not where gravity acts. The scale shift becomes gentle. On the smallest scales, a single photon scatters off an electron and changes direction. On larger scales, billions of scatterings create a diffusive glow. On larger scales still, the inner disk changes thickness as clumps arrive and merge. Over millions of years, repeated thick episodes can build a giant quickly. Over the same time, the outward appearance can remain subdued. The thick state does not last forever. Gas can thin as fuel is consumed or diverted. The mound can settle into a flatter layer. The surface becomes less opaque. Photons begin to escape more directly. The glow can brighten for a while even as inflow slows. This introduces a calm reversal. The fourth payoff lands. Brightness can increase after a feeding episode because stored heat finally leaks out. A system can look more active while it is actually easing into rest. A visual anchor shifts to the outer disk. A faint ring appears farther out than expected. The ring is not sharp. It is a broad band of slightly warmer emission. The band has a gentle gradient across its width. The gradient hints at heat being deposited from within. Energy transported outward by waves and turbulence warms the ring. Energy leaking outward from a thick inner mound can also warm it. The ring becomes a quiet echo of earlier inflow. Another payoff follows. The disk can carry memory in temperature layers. The inner mound can trap energy. The outer ring can later reveal it. The scene remains calm and free of drama. It is a slow redistribution of energy and mass. The limit of observation enters with clear specificity. Photon trapping is a process in the inner few light days or light weeks. At this distance, the inner structure cannot be resolved. The mound and ring are inferred from broad spectral shapes and from how brightness spreads. Dust emission and warm gas emission can overlap in wavelength. Models must assume the dust grain properties. They must assume the disk tilt. They must also assume how much energy is carried inward versus outward. Different assumptions can mimic the same softened glow. The limit is degeneracy between obscuration and trapping. A faint core could be hidden by dust. It could also be dim because energy is trapped. It could be both. Yet the concept remains useful because it provides a path to rapid growth without constant glare. It also fits naturally with bursty inflow. When a knot arrives, the inner flow can thicken. When the knot passes, the flow can thin. Light can be delayed in each thick phase. The sleeping appearance can then persist across many knots. A final visual anchor returns to the inner mound. The surface looks like a low dome with faint layered stripes. The dark lane across the mid-plane remains. The outer disk fades into a broader haze. The center stays a quiet absence inside a soft glow. The transition forward remains gentle. The next step turns to another guide inside the flow. It follows how magnetic fields can shape channels and help angular momentum move even when light is trapped. A dim disk can still be organized by an invisible thread that shapes motion from within. The anchor is that magnetic fields can move angular momentum outward and help gas drift inward without requiring a constant blaze. In that region, the flow is not only gas and dust, it is also charged particles that respond to fields. The scene begins with a quiet inner disk that looks faint and layered. A visual anchor forms as a braided texture in the glow. Two faint lanes run side by side. They twist slightly as they curve inward. Between them, a darker channel persists. The channel is narrow. It looks like a seam cut through soft fabric. The first payoff arrives with that seam. A disk can develop preferred pathways for transport. Those pathways can be guided by fields rather than by brightness. The first concept is magnetorotational instability. Magnetorotational instability means magnetism turns shear into turbulence. The definition stays brief and then returns to plain language. In a rotating disk, inner layers orbit faster than outer layers. A weak magnetic connection between layers can act like a tether. The tether pulls on the faster inner layer and drags on the slower outer layer. Energy and momentum exchange. The disk becomes turbulent in a controlled way. A calm analogy keeps the idea tangible without human presence. It resembles seaweed strands in a gentle current. When layers of water slide past, the strands stretch and transmit drag. The flow becomes rippled. In the disk, those ripples become a conveyor for angular momentum. The second payoff follows quickly. Turbulence is not only disorder, it can be the mechanism that allows inward drift. Without transport, gas would keep circling and stall. With transport, a fraction can slip inward while the rest carries momentum outward. A physical detail anchors the turbulence. The disk surface shows faint corrugations. Brightness rises and falls in narrow bands. The bands are not perfect spirals. They are slightly broken and patched. The breaks suggest eddies and waves. The inner rim remains thin. It retains a sharper edge than the outer haze. That edge implies that gas continues to be processed inward. Another payoff settles. The disk can feed steadily at a low level because turbulence keeps pathways open even during quiet phases. The second concept joins without crowding. Magnetic pressure adds support that can puff parts of the cell. Where fields strengthen, the disk can thicken slightly. Where fields weaken, it can flatten. This creates a layered appearance with subtle height changes. The light responds by scattering differently. Thicker regions scatter more and look softer. Thinner regions look sharper. A visual anchor deepens into the inner few light years. A faint fan of emission rises above the disk plane. The fan is not a jet. It is a gentle, broad plume of warm gas. Its edge is diffuse. It fades into the surrounding darkness. The plume hints that some energy and matter are lifted from the disk's surface. Fields can guide that lift. The payoff is immediate. A disk can lose some mass upward while still feeding inward below. This can keep the central brightness modest. It can also change how heat escapes. The plume can carry energy away. It can also create cavities that reduce opacity in some directions. Light behaves as a soft gradient across these layers. A signal would emerge stronger along a clearer path and weaker where the plume and dust thicken. The geometry then becomes part of the story. Magnetic structure can make the emission anisotropic. The same system can look more active from one angle and quieter from another. Another payoff follows. A sleeping label can partly reflect viewing angle when magnetic structure shapes thickness and escape routes. A single number grounds the magnetic idea without forcing detail. A magnetic ripple can organise a region about 1 light-year across. That is like the distance between the Sun and its nearest stellar neighbour. It is small compared with the galaxy and large compared with any planet. The scale shift follows gently. On microscopic scales, charged particles spiral around field lines. On macroscopic scales, those spirals add up to stresses that move momentum through the disk. Over thousands of years, stresses reshape rings and lanes. Over millions of years, they help bursts become possible. They also help quiet phases persist with slow feeding. A visual anchor shifts to the boundary between inner and outer disk. The outer disk looks puffed and dusty. The inner disk looks flatter and cleaner. Between them sits a narrow transition band with a steep brightness gradient. The band can be a region where magnetic activity changes. It can also be where temperature crosses a threshold that affects ionization. Ionization controls how well gas couples to magnetic fields. Ionization means atoms lose electrons and become charged. When coupling is stronger, turbulence is stronger. When coupling is weaker, the disk can become calmer and more layered. The payoff lands softly. The disk can switch between a more turbulent state and a more laminar state depending on temperature and composition. That switching can contribute to bursts. It can create zones where gas piles up. Then a change in coupling can release that pile inward. The limit of observation enters clearly. Magnetic fields cannot be mapped directly in such a distant, faint galaxy. The braided lanes and plumes are interpreted from light patterns. Many non-magnetic processes can create similar bands. Dust lanes can mimic seams, spiral density waves can mimic braids, scattering can blur edges. The limit is indirect inference. Models must assume ionization levels and disk thickness. They must assume how turbulence scales with field strength. Without resolved polarization or detailed line profiles, magnetism remains a plausible guide rather than a measured fact, and the concept remains valuable because it solves a specific problem. It provides a robust way to transport angular momentum. It works at low brightness. It can operate in both thin and thick disks. It can connect to photon trapping by shaping opacity and lift. Another payoff settles in that connection. A thick inflow can trap light. Magnetically driven turbulence can still move mass inward. The system can therefore grow during phases when radiation cannot push back efficiently. The present sleeping appearance becomes consistent with earlier rapid assembly. The final visual anchor returns to the braided lanes. They curve inward and fade near the dark centre. The faint plume above the disk becomes thinner with distance. The outer haze remains soft and dusty. The entire structure looks like a quiet pattern woven into a dim glow. Transition forward stays gentle. The next step turns from internal transport to the host itself. It follows how the galaxy's mass and light can lag behind the central mass, creating an early imbalance. A sleeping giant is most revealing when the surrounding galaxy looks too small for it. The anchor is that the central mass can outrun the growth of starlight in the early universe. The scene widens from the inner disk to the whole compact galaxy. The galaxy appears faint and tight. Its outer edge fades into a soft haze. The core remains darker than expected for a strong active centre. A visual anchor forms as a compact bulge wrapped in a thin envelope. The bulge is slightly brighter on one side. A dusty lane crosses near the midplane and softens the core. Around the bulge, a faint halo extends outward like a pale mist. The first payoff arrives. A large black hole does not require a mature galaxy with a long, settled history. In the early universe, the center can assemble quickly while the larger structure lags. The first concept is scaling relation. A scaling relation is a link between black hole mass and bulge mass. The definition stays short and then returns to plain imagery. In nearby galaxies, bigger bulges tend to host bigger central black holes. It is not a perfect rule. It is a trend built over time. In a young compact galaxy, the trend may not yet be established. A calm analogy keeps the idea gentle. It resembles a river delta that has not yet spread out. A deep central channel can form first. The broad fan of sediment builds later. The second payoff follows. A mismatch between center and host can be a sign of timing rather than an error. The second concept is star formation efficiency. Star formation efficiency is how well gas becomes long-lived stars. Gas can be plentiful and still not become starlight quickly. Turbulence can keep gas stirred. Heat can keep it puffy. Dust can hide it. Feedback can delay collapse. The galaxy can therefore remain faint while gas continues to exist. The black hole can grow during short episodes that do not immediately translate into a brighter bulge. Another payoff settles. A quiet galaxy can still contain a large reservoir and a large hidden center. The physical details of the host offer clues. The galaxy shows patchy brightness. Small knots of light appear along one side. The knots are embedded in a diffuse glow. The glow is smoother near the center and more irregular toward the edge. A gentle gradient runs outward. The center is warmer and the outskirts are cooler. Dust scattering blurs the inner boundary and turns sharp knots into soft patches. A visual anchor deepens. A faint arc of emission sits slightly off-center, as if a ring is forming but not complete. The arc has a brighter segment where gas density is higher. It fades where dust thickens. The arc suggests a rotating structure that has not yet settled into symmetry. The third payoff arrives from that asymmetry. Early galaxies are still assembling. Their bulges and disks are unfinished. A central mass can find fuel in that unfinished structure. Streams and clumps can funnel gas inward before the bulk of gas becomes stars. A single number anchors the mismatch without forcing precision. The ratio of black hole mass to bulge mass can be about 1% in this kind of system. That is like a pebble that weighs as much as an entire handful of sand. In nearby mature galaxies, the ratio is often smaller. The payoff is immediate. The center appears overweight compared with the visible host. That overweight state suggests an early phase where black hole growth is ahead of stellar buildup. The scale shift stays gentle. On the inner scale, gas circulates around the dark core and feeds in bursts. On the galactic scale, gas must cool and fragment to form stars. Cooling can be slowed by heat and turbulence. Fragmentation can be delayed by shear. In the intergalactic environment, filaments deliver fresh gas unevenly. Over tens of millions of years, the center can gain mass rapidly during a few bursts. Over the same interval, the galaxy's starlight may rise only slowly if star formation is inefficient or hidden. Another payoff settles into the timeline. A mismatch can persist long enough to be observed because the host builds more slowly than the center. The mismatch also changes how the galaxy evolves. A massive center deepens the central gravity well. Gas in the inner region experiences stronger tides. It can be stretched into streams. It can form rings with sharper inner edges. It can develop a steeper density gradient toward the center. Those physical features can influence where stars form later. Star formation may move outward into rings. It may avoid the deepest center where tides are strong. A visual anchor shifts to the inner few hundred light years. A faint ring-like structure appears as a broad band. The band is cooler and dustier than the inner rim. It looks like a belt with a smooth inner boundary. The belt contains a few brighter knots. Between knots, the belt stays dim. The belt suggests gas collecting where rotation and pressure balance. The next payoff follows. A heavy center can encourage gas to pile into rings. Rings can form stars later after enough cooling and compression. The bulge can therefore appear faint now and brighter later. The mismatch can narrow over time. The limit of observation enters softly and precisely. Bulge mass is inferred from light. Light is affected by dust and by age of stars. A young population can be bright per unit mass. An older population can be dimmer. Dust can hide a large fraction of starlight. Gas mass is not directly visible in the same bands. The black hole mass is also inferred indirectly through models of light and motion. Both estimates depend on assumptions about geometry and composition. The limit is uncertainty in mass to light conversion and in obscuration. A high ratio can be partly real and partly amplified by hidden starlight. Yet even with uncertainty, the idea of early imbalance remains plausible. The core appears too massive for the visible host at this epoch. Another payoff settles. If many early systems share this imbalance, then black hole growth may begin before galaxies fully mature. That changes the meaning of a sleeping giant. It becomes a relic of earlier rapid growth that the host has not yet matched. The final visual anchor holds the whole compact galaxy in view. The faint bulge sits inside a soft envelope. The incomplete arc suggests a forming ring. Dust lanes soften the core and smear the edges. The center remains quiet and heavy inside this unfinished structure. The transition forward stays gentle. The next step turns to the memory of earlier bright phases. It follows how past activity can heat and stir gas, delaying starlight and deepening the mismatch. A quiet center can still leave a warm fingerprint across the host long after the bright phase ends. The anchor is that feedback can heat and stir gas, delaying starlight while the black hole remains massive. The view holds the compact galaxy as a whole. Its light is patchy. Its core is muted by dust. Its outer edge fades into a thin haze. A visual anchor forms as a faint bubble-shaped region around the center. The bubble is not a sharp shell. It is a gentle cavity where emission looks slightly weaker. Around the cavity, a thin rim looks marginally brighter. The rim is uneven. It has a brighter segment and a dimmer segment. That shape suggests gas pushed outward in an earlier episode. The first payoff arrives. A bright path can be detected as structure even when present brightness is low. The first concept is feedback. Feedback is energy from the center affecting surrounding gas. The definition stays short and then returns to imagery. When the inner flow radiates strongly, it can heat nearby gas. It can also drive a wide outflow. The outflow does not need a narrow beam. It can be a broad wind of hot gas and radiation pressure. In a dusty young galaxy, that push can carve cavities. It can compress gas into rims. It can also mix dust into thicker lanes. A calm analogy keeps it natural and quiet. It resembles a gust over a shallow dune field. The sand does not vanish. It shifts into ridges and hollows. Later, even in still air, the pattern remains. The second payoff follows. A sleeping present can sit inside a landscape shaped by earlier winds. The physical details of the rim matter. The rim shows a brightness gradient across its thickness. The inner side is sharper. The outer side is softer. That gradient suggests compression at the inner edge and diffusion outward. Dust scattering smooths the outer boundary. The rim is also not circular. It is slightly stretched, hinting at uneven density in the surrounding medium. Where gas is denser, the cavity expands less. Where gas is thinner, it expands more. Another payoff settles. The shape of a cavity can reveal the texture of the host gas. The second concept is cooling time. Cooling time is how long hot gas takes to radiate heat away. In a young galaxy with low heavy element content, cooling can be slower in some phases. In a dusty region, cooling can be more complex because dust grains re-radiate energy at longer wavelengths. Either way, hot gas can stay hot for a long span. That means a bright episode can keep gas puffy long after the light fades. A single number anchors the sense of persistence. A heated cavity can last about 50 million years. That is like the time it takes a continent to shift a noticeable distance. It is long compared with a burst. It is short compared with the age of a mature galaxy. The payoff is immediate. A quiet snapshot can still be within the aftermath window of a past outflow. The scene shifts scale gently. Near the center gas is heated and pressurized. It expands and lowers its density. Lower density reduces star formation because clouds struggle to collapse. Farther out, the outflow slows and the gas can pile up into a rim. The rim can become a ring of denser material. Over millions of years, that ring can cool and fragment. It can begin forming stars later away from the cavity. The quiet giant thus reshapes where future light will appear. Another payoff emerges. Feedback can delay the host's visible growth, deepening the mismatch between center and bulge for a while. A visual anchor deepens into the dusty lanes. A dark band crosses the inner region and splits into two thinner lanes. The lanes curve around the cavity rim. Their edges look frayed. The fraying suggests turbulence. Small knots sit along the lanes like faint beads. The knots are not bright enough to dominate. They hint at gas that is denser and cooler in small pockets. The third payoff follows. Even within a heated environment, some pockets can survive and begin to cool. The galaxy becomes a layered mix of hot cavities and cool knots. Light behaves as a softened mix of emissions. Warm dust glows broadly. Cooler dust glows more faintly. Ionized gas can add a thin haze in some bands. The present quiet core adds little to that mix. The mix can therefore be dominated by the host's afterglow rather than the center's current output. Another payoff arrives. A sleeping black hole can be hidden inside a galaxy that still glows from its own rearranged gas. The limit of intuition enters with a specific edge. Feedback is inferred from morphology and from broad spectral features. At this distance, separate components blur. A cavity can be mimicked by patchy dust absorption rather than real gas removal. A rim can be mimicked by a chance alignment of star-forming knots. Cooling time depends on metallicity and density that are not directly measured with precision. Models must assume how much energy a past burst delivered. They must also assume how efficiently it coupled to gas. The limit is ambiguity between geometry and physics. Still, the cavity and rim pattern remains a plausible signature because it connects multiple constraints. It explains a quiet present. It explains delayed bulge growth. It explains patchy star formation in rings and knots. Another payoff settles into the timeline again. If feedback episodes repeat, the galaxy can spend long intervals in a stirred state. Star formation becomes intermittent. The bulge grows in steps. The black hole grows in steps too. The steps need not match. The mismatch can persist at early times and then narrow later as gas settles. A visual anchor shifts outward to the rim zone. The rim appears as a broad, incomplete ring. One side is brighter and sharper. The opposite side fades. The ring suggests gas that is denser where the outflow meets a thicker region. Along the brighter segments, small clumps form a chain. Between clumps, the ring is smooth. The chain hints at fragmentation beginning but not yet complete. The payoff is immediate. A past push can create the conditions for later star formation by compressing gas at the boundary. The same process that delays collapse near the center can encourage collapse in a ring. The scale shift returns in time. The outflow's push happens on short scales compared with galaxy assembly. The cavity persists over tens of millions of years. The ring builds and fragments over similar spans. The full bulge emerges over hundreds of millions of years. The sleeping present sits somewhere along that slow recovery. The close-in transition remains gentle. The next step turns from feedback patterns to the hidden population question. It asks how many other massive quiet centers may exist at early times and how selection effects shape what appears in view. A quiet discovery hints at a much larger hidden population beyond the small number that stand out. The anchor is that selection effects can hide many sleeping giants because faintness and dust mask them. The view widens again to the early universe background. Many compact galaxies sit as soft smudges. Only a few show clear central signatures. A visual anchor forms as a field of faint objects. Some are round and smooth, some are stretched and patchy. Between them, darkness holds long intervals with no visible structure. In one compact system, a subtle central haze is present. In most others, the center blends into the host light. The first payoff arrives. The rare detected case may be only the visible tip of a broader family. The first concept is selection bias. Selection bias is a tendency to detect only certain kinds. The definition stays brief and then returns to plain imagery. A survey is like a net with a specific mesh size. Large fish are caught, small fish slip through, in the same way bright active centers are caught easily. Dim or dust-covered centers slip through. The analogy stays natural and calm. It does not require human presence in the scene. The second payoff follows at once. A sleeping giant can be common and still appear rare because the view favours bright phases. The physical details of detection matter. A compact galaxy can have a bright core that is smeared by dust into a broader patch. That patch can be mistaken for ordinary starlight. The central region can also be hidden behind a dark lane. The lane has a sharper inner edge and a softer outer edge. Scattering makes the lane boundaries fuzzy. This means the core signature can be muted in exactly the region where it matters most. Another payoff settles. Dust does not need to be perfect to hide a signature, it only needs to reduce contrast. The second concept is luminosity function. A luminosity function is the count of objects by brightness. The definition stays short and then returns to calm logic. If most black holes spend little time bright, then the luminosity function at early times is steep. There are many faint objects and few bright ones. The bright ones dominate attention. The faint ones dominate numbers. This leads to a quiet inference. The discovered sleeping case implies a lower floor of activity is detectable. That floor suggests there may be many more below it. A single number anchors the scale of hiddenness without overspecifying. A typical bright phase might occupy about 1/10 of the time. That is like a shoreline that is underwater only during the highest tides. Most of the cycle is exposed and quiet. The payoff is immediate. If bright phases are brief, then most objects are caught in quiet states. A field of early galaxies can therefore host many massive centers that do not announce themselves. A visual anchor deepens into one ambiguous galaxy. Its light is smooth. The core is slightly warmer in color. The warmth is subtle. A faint ring-like band sits off-center. The band is incomplete. It fades behind a dust lane. The dust lane breaks into smaller filaments. These filaments add mottled texture. The mottling can mimic star-forming patches. It can also hide a compact core. The third payoff arrives. Morphology alone can be misleading at this distance. A center can be present and still look like ordinary structure. The scale shift becomes gentle. On small scales, the inner disk and broad line region would reveal motion. At this distance, those regions are unresolved. On larger scales, the host light is integrated into one blur. Over time, bright phases flicker on and off across millions of years. A single snapshot catches only one phase. A survey catches a mix of phases, but still favours the brighter ones. This creates a quiet mismatch between what exists and what is catalogued. Another payoff follows. The census of early black holes is likely incomplete, especially for sleeping cases. The limit of observation enters clearly. Faint objects are limited by sensitivity. Dust-covered objects are limited by wavelength coverage and by confusion with host emission. Redshift moves key features into bands where background noise can be higher. In some cases, the best diagnostic lines are too weak to separate from the galaxy continuum. In other cases, the continuum itself is dominated by warm dust that can mimic an active signature. The limit is degeneracy and threshold. Below a certain brightness, contrast the core cannot be distinguished. This makes the luminosity function at the faint end uncertain. It also makes duty cycles uncertain. Yet a single detected sleeping giant provides a constraint. It suggests that massive centers can exist without bright signatures. That raises the probability that many more remain unseen. A visual anchor shifts to the cosmic web. Filaments appear as extremely faint gradients in the background. Compact galaxies sit at the nodes. If gas delivery is common along filaments, then many nodes can feed black holes at least occasionally. If many nodes feed occasionally, then many black holes can grow. Most of them may be quiet most of the time. The fourth payoff arrives from this network view. The early universe can build a broad base of massive centers even if only a few are caught shining. The section then adds a careful consequence. If the hidden population is large, it changes how reionization and heating proceed. It changes how feedback operates on average. It also changes expectations for future surveys. A deeper search would uncover more sleeping cases. A wider search would find more rare bright bursts. The distribution of both would reveal duty cycles. The final payoff becomes a calm promise. A sleeping discovery is not only an isolated curiosity, it is a clue about missing members in the early census. The closing visual anchor returns to the faint field. Most galaxies remain soft and quiet. A few show subtle warm cores. The dark lanes and incomplete rings hide and reveal in equal measure. The universe looks like a tapestry where only some threads catch light. The transition forward stays gentle. The next step turns from population to measurement. It follows how mass is inferred from spectra and broad features and where those inferences can be strong or fragile. A massive quiet center is known through indirect traces that must be weighed with care. The anchor is that broad emission lines and surrounding glow can hint at mass, yet geometry and dust shape the inference. The scene narrows back toward the compact galaxy core. The central region is not a point. It is a soft knot inside a dusty bulge. A visual anchor forms as a faint halo around the nucleus. The halo is bright on one side. It fades into the bulge on the other side. A narrow dark lane crosses the halo and creates an asymmetric bite. The first payoff arrives. Even when the center is dim, the environment can carry signatures of fast motion and ionized gas. The first concept is broad line region. Broad line region means fast gas close to the center. The definition stays brief and then returns to imagery. Gas near the center moves rapidly in tight orbits. That motion spreads an emission line into a wide feature. The width is a measure of speed. Speed is a measure of gravity. The analogy remains calm and natural. It resembles wind across a wide reed bed. Some stalks sway gently, some whip faster near the strongest gust. The overall motion appears broadened when seen as a blur. In the same way gas nearer the center broadens the line. The second payoff follows. A broad line can hint at a deep gravity well even if the continuum is faint. The physical details of the halo matter now. The halo has a gradient. It is brighter near the center and softer outward. The edge is not sharp. It fades into the bulge like mist. That suggests ionized gas filling a volume rather than sitting in a thin shell. The dark lane implies dust mixed with gas. Dust can block parts of the halo. It can also scatter light into a wider glow. Light behaves as a combination of direct emission and scattered emission. A signal would therefore be a blend, not a pure core. Another payoff settles. Dust can hide the true center while still allowing broad gas signatures to leak out. The second concept is virial estimate. Virial estimate means mass inferred from speed and size. The definition stays brief and returns to plain logic. If gas is bound, its speed relates to the central mass and its radius. The mass can be estimated from the line width and an estimate of the region's size. The size is often inferred from luminosity. That introduces a quiet complication. If luminosity is dimmed by dust or by sleep, the size estimate can shift. If geometry is tilted, the measured speed can shift. Yet the method still provides an order of magnitude. The third payoff arrives. Even uncertain estimates can distinguish a modest centre from a truly enormous one. A single number anchors the story with care. A mass near 400 million solar masses is the weight of about 400 million suns. That is like stacking hundreds of millions of warm lanterns into one invisible pile. The payoff is immediate. Such a mass is too large to be explained by small fluctuations. It demands substantial earlier growth. The scale shift follows gently. At the scale of the broadline region, distances are measured in light days to light weeks. Motion there changes on short times. At the scale of the galaxy, dust lanes and rings evolve over millions of years. At the scale of cosmic time, the system is seen only once. The single spectrum is a frozen moment that must represent a whole history. A visual anchor deepens into the line-forming gas. The region is imagined as a thick set of orbiting streams. The streams are not smooth. They are clumpy and layered. Each layer has a slightly different density. The inner layers are hotter and more ionized. The outer layers are cooler and dustier. Boundaries form where ionization changes. Those boundaries can act like thin surfaces where particular lines brighten. The payoff lands. The spectrum is a map of layers in velocity space rather than a picture in ordinary space. The method turns velocity into structure, yet uncertainty remains. The limit of observation becomes specific and gentle. The broad line width depends on orientation. If the motion is in a flattened distribution, viewing angle changes the apparent width. The size estimate depends on luminosity that can be dimmed. Dust reddening can alter the continuum and bias the size proxy. The host galaxy light can contaminate the core light. At high redshift, lines can blend with nearby features. The resolution sets a floor under how well line shapes can be separated. The limit is degeneracy between dust geometry and true size. Different combinations can reproduce similar observed widths and luminosities. Still, the presence of very broad gas features suggests fast motion close in. The inference of a large mass remains plausible within a range. Another payoff follows. The sleeping label does not require exact mass. It only requires that the mass is large compared with the quiet output. A visual anchor shifts to the surrounding ionized region. The halo shows filaments. They are faint and thin. They extend outward like wisps. Their edges are soft. They fade into the bulge. The filaments can be illuminated by a weak present core. They can also retain ionization from earlier brighter phases if recombination is slow in low-density gas. Recombination is ions regaining electrons. The definition stays brief and then returns to imagery. In thin gas, recombination can be slow, the glow can linger, the payoff is immediate. The environment can act like a dim after-image of earlier radiation. That complicates the interpretation of current activity. The present core may be weaker than the halo suggests. Another payoff settles. A quiet center can be measured by indirect echoes that integrate over time. The scene then ties the measurement back to the global arc. A large inferred mass supports the earlier sections about bursty growth, photon trapping, and magnetic transport. It also supports the host mismatch. The measurement is the hinge between story and physics. It remains cautious. It stays order of magnitude safe. It respects the limits of distance and dust. The closing visual anchor returns to the asymmetric halo in its dark lane. The halo glows softly. The lane cuts across like a calm shadow. The core sits behind it with muted light. The transition forward stays gentle. The next step moves to the widest perspective again. It follows how these sleeping giants fit into the long arc of cosmic history. and what a quiet present means for the future of the host. A sleeping giant sits inside time, and time keeps moving around it in slow waves. The anchor is that the same mass that grew early can shape the galaxy's next billion years even in quiet. The scene opens on the wider environment again. A compact galaxy drifts near another faint neighbour. Between them, a thin bridge of dim material spans the gap. The bridge is uneven. It has thicker knots and thinner strands. The first payoff arrives. Early growth does not end the story. It sets the next conditions for gas and stars. The first concept is gravitational potential. Gravitational potential is the depth of a gravity well. The definition stays brief and returns to imagery. A deep centre changes how orbits curve. It also changes how gas settles. In the inner region, tides stretch clouds. Streams become narrower. Rings become sharper at their inner edges. A visual anchor deepens on the bridge. The bridge looks like a pale ribbon. It bends into a shallow S shape. Dust inside it creates darker seams that run along its length. Where the seams cross thicker knots, the knots glow slightly warmer. The second payoff follows. Interaction and inflow can happen without a blazing centre. A massive core can be ready to respond when fresh gas arrives. The second concept is gas supply. Gas supply is the amount of fuel reaching the inner region. The definition stays short and returns to plain logic. Fuel can arrive in clumps, fuel can arrive in streams, fuel can also arrive as a slow drizzle from the host's own reservoir. When the supply is low, the centre can remain dim. When supply rises, the centre can brighten again. The consequence is calm and direct. A sleeping phase is compatible with future wakes. Another payoff settles. The same object can alternate between quiet and bright while keeping the same mass. The physical details of inflow appear in the host. The inner disk shows a faint ring. The ring has a clean inner boundary and a softer outer fall-off. A narrow dust lane grazes the ring and blurs one segment. The blurred segment looks thicker. The unblurred segment looks thinner and sharper. This suggests uneven opacity rather than uneven mass alone. Light behaves as a softened mixture of emission and absorption. A signal would look different from different angles because dust changes contrast. The next payoff arrives. A centre can appear steadily quiet while small feeding events occur behind dust. The scale shift becomes gentle. Close-in orbital times can be short. A ring can rearrange within thousands of years. Far out, the bridge between galaxies evolves over tens of millions of years. On cosmic scales, 1 billion years passes as a single chapter. 1 billion years is like the span between very ancient eras on Earth. It is long enough for a galaxy to change its shape. It is also long enough for repeated feeding cycles. Another payoff follows. A single early massive centre has ample time to influence many later phases. The visual anchor shifts from bridge to outskirts. The outer envelope shows a faint lopsided glow. One side fades more quickly. The other side extends into a low surface brightness tail. The tail is broad. Its edge is diffuse. It suggests material being stirred and redistributed. The third payoff arrives. Distribution can build the bulge and smooth the host over time. Gas that is stirred can later cool and settle. Stars that are scattered can puff up the central region. The host can catch up to the centre slowly. The analogy stays calm and natural. It resembles 2 drops of ink meeting in still water. At first there are sharp streaks. Later the colour spreads into a smooth gradient. In the same way, an early compact host can become more extended and uniform. The fourth payoff follows. The present mismatch between centre and bulge does not need to persist. It can narrow as the host builds. The section then turns to feedback as a long-term regulator. A massive emitter can create strong episodes when fuel is abundant. Those episodes can heat and stir gas. Heat delays collapse into stars near the centre. Stirring can move star formation outward into rings. Over time, that can build a galaxy with a calmer core and a more active outer zone. Another payoff settles. A giant center can help carve where future starlight prefers to form. The physical details support that picture. The inner region shows a cavity-like softness. It is not a hole, it is a slightly lower brightness zone. Around it sits a thicker band. The band is warmer and dustier. The band has small knots spaced along it. Between knots, the band is smooth. The knots are the same scale all around. This suggests a preferred fragmentation length. Another payoff arrives. Gas can collect into rings and fragment in a repeatable pattern. The pattern is set by gravity and pressure. The center's gravity matters because it sets orbital shear. The band's thickness matters because it sets pressure support. Together they set where knots can survive. The scale shift returns to the smallest parts. Within knots, dust grains scatter and re-radiate energy. Within knots, cooling allows denser cores to form. Yet the deep tide near the center can pull those cores apart. The result is a zone where clouds are stretched rather than collapsed. That is a quiet form of regulation. Another payoff follows. A massive center can regulate star formation without being bright at the moment. The limit of observation enters clearly and softly. Future evolution cannot be observed directly in this single system. The bridge may not lead to a full merger. It may disperse and fade. The gas supply may rise or fall unpredictably. The duty cycle of bright phases is inferred rather than measured here. Dust geometry can mimic cavities and bands. The limit is prediction from one snapshot plus incomplete census. Models must assume typical interaction rates at this epoch. They must assume how gas cools in young galaxies. They must assume how feedback couples to dusty gas. Even so, the broad arc remains plausible. A massive early center can persist through many cycles. The host can slowly assemble around it. Another payoff settles. The discovery adds a missing mode to early cosmic history. Massive centers can exist in quiet states. That means growth can be hidden and intermittent. The calm conclusion begins to form. A sleeping phase is not a pause in cosmic evolution. It is one state in a long alternating rhythm. The visual anchor widens one last time. The faint bridge becomes thinner. The tail becomes a softer haze. The compact core remains muted behind dust. The outer envelope gradually smooths into a rounder glow. The scene feels slow and stable. The transition forward stays gentle. The next step closes the journey with a soft perspective. It rests on what a quiet giant means when viewed across deep time. A quiet black hole becomes most revealing when it is placed inside the long calm of cosmic time. The anchor is that a sleeping phase can be ordinary, and the universe can still build immense mass early. At this distance, the galaxy is seen as a compact glow with a muted heart. The center is not a sharp point. It is a softened knot behind a dusty veil. A thin, dark lane crosses the inner light. The lane has a crisp inner edge. It has a feathered outer fade. Around it, a faint halo spreads in a gentle gradient. The first payoff arrives. A sleeping giant can be present without dominating the scene. The first concept is look-back time. Look-back time is the time light needs to arrive. The definition stays brief. The image returns to quiet motion through space. Light leaves a young galaxy. It travels across expanding darkness. It arrives carrying an old state. The present view is therefore a memory. The next payoff settles quickly. A sleeping phase seen now can belong to a long cycle that continues unseen. The field widens to the surrounding sky. Many faint galaxies sit like soft embers. Their shapes are small and varied. Some are nearly round, some are slightly stretched. A few show faint tails that dissolve into darkness. Between them, the background is not empty. It holds a smooth glow that barely changes. This becomes a visual anchor. A broad sheet of dim light fills the scene like fog over a plain. In that fog, the compact galaxy is one quiet ridge. The second payoff arrives. A single discovery is also a clue about the unseen majority. The second concept is accretion. Accretion is gas falling inward under gravity. The definition stays brief and returns to plain imagery. Gas does not fall as a straight line. It circles and flattens. It forms a rotating flow with a layered structure. The flow can be thin in some regions, it can be puffed in others. Dust can mix in the outer layers. Dust can create shadowed bands. Those bands change what is visible. Another payoff follows. Accretion can continue softly while light is muted by dust and geometry. The inner region is imagined in slow detail. A faint ring-like band sits within the host. The band is not complete. It breaks where the dust lane crosses. One side is brighter, the other side is dimmer and broader. The boundary between bright and dim is a smooth gradient. This is a physical clue. Gas and dust are not arranged evenly. They form layers and seams. The third payoff arrives. Uneven structure can hide a central engine without removing it. A gentle scale shift begins. Closing gas motions change quickly. Small clumps shear and stretch in short times. Farther out, the host changes slowly. Rings drift and thicken over long epochs. Far beyond the host, the cosmic web evolves on deeper timescales. Filaments feed nodes. Nodes merge and separate. The view holds all these scales at once. Another payoff settles. A quiet nucleus can still sit at the center of an active cosmic neighborhood. The scene returns to the core. The halo around the nucleus is asymmetric. It is brighter on one side, it fades into the bulge on the other. The halo edge is not sharp, it dissolves like mist. Thin wisps extend outward. Their edges are soft, their brightness is low but coherent. Light behaves as a blend of direct emission and scattered emission. A signal would therefore carry mixed information. This becomes a calm limit of intuition. It is easy to imagine a single source. It is harder to separate layers without ambiguity. The limit of observation is also specific. At high distance, small regions are not resolved. Line shapes blend with continuum. Dust reddening alters apparent brightness. Orientation changes the apparent widths of features. These effects can mimic each other. The limit is degeneracy between geometry and true power. The next payoff arrives. Even with uncertainty, a massive quiet center remains plausible when multiple hints align. The story holds one simple mental number and lets it breathe. The universe is about 13 billion years old. That is like a desert forming from countless grains carried by wind. The comparison stays natural and quiet. It offers scale without sharpness. The payoff follows. A short, bright episode can be a tiny fraction of that span, and most time can be calm. The view widens again to the field of faint galaxies. Most appear ordinary. Most do not show obvious blazing centers, yet many may host large masses that are simply quiet. The sleeping case becomes a representative state rather than an exception. Another payoff settles. A census based only on bright phases cannot capture the full population. A new visual anchor replaces the earlier fog sheet. A long, gentle arc of distorted background light curves near a cluster of faint smudges. The arc is thin and pale. It is sharper on one side. It softens on the other. The curve suggests bending by mass. It also suggests that mass can be present without glow. The payoff arrives. Gravity leaves traces even when light is subdued. The arc is only an image, yet it mirrors the logic of the discovery. Mass is inferred from effects, not from direct brightness alone. The scene then becomes calmer and slower. The compact galaxy remains small. The dust lane remains steady. The halo remains faint. The center remains quiet. In that quiet, the arc of cosmic history becomes easier to hold. Early growth can be fast at times. It can be hidden at other times. It can proceed in bursts that leave after images in surrounding gas. Then it can rest again. Another payoff follows. The sleeping label is not a contradiction. It is a phase in a broader rhythm. The scale shift returns one last time. Within the innermost region, motion is swift. Within the host, evolution is slow. Within the universe, history is vast. The same object spans all three. It sits as a deep gravity well in a young galaxy. It will remain a deep gravity well as the galaxy matures. The future cannot be seen from this single frame. Yet the arc can be framed without strain. Quiet phases are likely common. Bright phases are likely intermittent. Dust and distance hide many cases. Another payoff settles. The discovery is a gentle reminder that absence of glare is not absence of mass. The closing image becomes simple and steady. The compact galaxy is a soft ember behind a veil. The dust lane is a calm shadow line. The halo is a faint breath of light. Beyond it, the background glow is smooth and unhurried. The story narrows to stillness. The universe keeps expanding. Light keeps travelling. The sleeping giant remains, whether bright or dim. The ending stays soft. The next moment is only a quieter continuation of the same long night.